can just wait and see. Someone can share what was the absolute magnitude you found for HV 2063. So Bailey got around -4.3. I think I got around -4.1, but somewhere around there. So yeah, the idea is because Cepheid variables have this nice relationship where brighter Cepheid variables have longer periods, we can use measurements of the period of a Cepheid variable to figure out the absolute magnitude. And then we can compare that to the apparent magnitude, which you can kind of measure on this graph. You can see there's measurements of the apparent magnitude on the y-axis. And we can use that to find a distance. So that's that last question, why are Cepheid variables so valuable? Is that we can use Cepheid variables to find the distance to stars. So this should look somewhat like the plot you made, where we have absolute magnitude on the y-axis and period on the x-axis. And they've changed the scale a little bit, so their period is logarithmic here. This is not a linear scale. You probably did it in a linear scale, which is fine, and what I expected. So you might have seen a little bit more of a curve instead of a straight line. But what we find is that there's a relationship between the period and the luminosity. So more massive stars take longer to expand and contract. More massive stars also happen to be brighter. So if I had two of my Cepheid toys, and one of them was bigger, the bigger one, it would take me longer to expand it and contract it. And so it would have a longer period because bigger stars are also brighter. So more massive stars are brighter. Brighter Cepheids have longer periods. So we get this nice relationship between period and absolute magnitude for Cepheids, which allows us to use Cepheids to find distances. So let's focus on the first part of this question. So I'm going to launch a poll now. I've listed a few Cepheid variables and their apparent magnitude along with their period. I want you to tell me which of the Cepheid variables is actually the brightest. So not the Cepheid variable that appears the brightest, but which of these four is actually the brightest, has the brightest absolute magnitude. So you should be seeing a poll where you can vote now. And I didn't write the names of the stars out because they're too long, so they're just 1, 2, 3, and 4. It looks like a little over half of us have voted. Let's focus on that first question especially, which, with the information I have shown you, which one is going to be the brightest? And not appears the brightest, but is actually the brightest. So which one would have the brightest absolute magnitude? Maybe 20 more seconds. Okay. So we're maybe not quite sure yet. It looks like there's still a bit of a scatter. What we can remember, the brightest Cepheids will have the longest periods. So the Cepheid with the longest period will be the brightest, which means Zeta Geminorum with the period of about 10 days is going to actually be our brightest Cepheid variable, even though its apparent magnitude isn't that different than the first three. So Delta Cephei is going to actually be the faintest because it has the shortest period. So shortest period will be fainter, longer period will be brighter. And that's the most thing we want to look at when we want to find the absolute brightest. The closest is a bit trickier because then you have to compare sort of which one looks the brightest and which one is actually the brightest. So the first three at least all have similar apparent magnitudes, so they all look similar brightnesses despite the fact they are not all the same brightness. So that might mean of the first three, Eta Aquilae is probably the closest because it's the same, looks to be the same brightness despite having a shorter period, meaning it is actually fainter. But Delta Cephei is a little bit more complicated because it has a shorter period, but also a higher magnitude. So it looks fainter, but it also is fainter. So it's kind of tricky to tell. Any questions about that, how we find that out? So one thing that I think is super cool about Cepheids is how we actually were able to use Cepheid variables to measure the distance to the nearest galaxies. So parallax shifting only works with really nearby stars. Cepheid variables are bright enough that we can measure their periods as they get further away, even in other galaxies. So this is how we initially measured the distance to our nearest neighbor galaxy, the Large Magellanic Cloud, which is what is shown here, this little fuzzy speck. If you are ever in the southern hemisphere, you can see the Large Magellanic Cloud. It looks kind of like a bit of haze in the sky. So if you ever go to Australia or anywhere in South America, you can see the Large Magellanic Cloud. And the person who initially did this was Henrietta Leavitt. So the relationship between period and luminosity of Cepheids is sometimes called the Leavitt law, after Henrietta Leavitt, who found it. And Henrietta Leavitt is one of the Harvard computers who some of you have done the Star Notes citizen science project, where you look at transcribing the note of the female astronomers who worked at Harvard in the early 1900s, and Henrietta Leavitt was one of those, and she found this relationship between period and luminosity of Cepheids and was able to use that relationship to measure the distance to the Large Magellanic Cloud, showing that galaxies were even further away than we realized. So that started a debate about what galaxies actually are, which we'll get to talk about more as we get into our next badge. So this is how we can kind of start to measure distances. So we can use parallax shifting, so the amount of shift a star does as we move around the sun to measure the distance to nearby stars. And then we can use Cepheid variables and the period luminosity relationship in Cepheid variables to measure the distance to Cepheid stars, as well as the galaxies that Cepheid stars are in. So Cepheids are a little brighter, so we can get kind of a slightly further objects. We can get distance to slightly further stellar clusters, ones that might not actually have parallax shifts, but they do have Cepheids, and we can measure these periods and compare the apparent magnitude, the magnitude of the Cepheid we see, with the absolute magnitude that we can determine using the Cepheid period luminosity relationship. This is another option where there's a lab where you get to do this a little bit more. So our last lab for this section is the variable star lab, which will use both Cepheid variables as well as binary stars, which we'll talk about at the end of today and maybe a bit next class. So if you're interested more in how we can use Cepheid variables to measure distance, that would be a good lab to explore that a little bit more. Before I move on, are there any questions about cepheids or parallax or how we measure distances to stars? So the next type of variable star we will discuss is going to be binary stars. So these are not stars that are necessarily changing brightness, but they're stars where we have two stars orbiting each other. And so this pair of stars will look like they're changing brightness as they move in front of and behind each other over time. So it's kind of a variable star, sort of something else. It's just two stars orbiting each other. Binary stars are super useful because we can use how long it takes for the two stars to orbit around each other to find the mass and the radiuses of the stars. So I said we were going to measure distances, masses, and radiuses of stars. Binary stars are going to be really useful when we want to measure those masses and radii. In order to look at binary systems, we need to be sure we're measuring two stars that are actually orbiting each other and not just two stars that look like they're close. So that means that a lot of times when you look up in the sky at night, you might see a few stars. Some stars look close to each other, but they could actually be really, really far apart if they are not the same distance from us. So two stars that are close to each other but not the same distance from us won't be a binary system. So you need to find two stars that are actually close. They don't just appear close, so they actually have to be orbiting each other. And if you can find two stars that are orbiting each other, which a lot of stars are in binary systems, so this is not that difficult to do, then you can use Kepler's laws and Newton's law of gravity to find the masses of the stars. So we can measure their orbit, measure the conditions of the parameters of their orbit to figure out the masses of the stars. As an example of a binary system, one of the first observed binary systems is Algol. And this is a binary system that is bright enough it can be seen by the naked eye, and you can sort of see it changing in brightness over time. And what's kind of cool about Algol is that one of the stars is actually leaking material onto the other, and that causes kind of funky changes in brightness over time, not just because of the stars are blocking out each other as they orbit each other, but they actually are exchanging some mass. And so that led to early astronomers to name Algol the demon star, because it's kind of red and it has weird changes in brightness over time. And they could actually measure the variabilities in brightness without a telescope, so making it one of the first variable stars discovered, which is pretty neat. And you know, we're getting close to Halloween, so gotta throw in the demon star. But what's more important is that we can measure mass and radii of stars by looking at the light curves we see from binary star systems. So our binary systems will rotate orbit around each other, and the amount of time it takes for them to orbit and the size and the distance between the two stars will allow us to use Kepler's third law to find the masses of the stars. So if we can observe the period, which we saw we could sort of with cepheids, it'll be kind of similar with binary stars. If we can observe the period, and if we can observe the distance between the two stars, the axis of their rotation, then we can actually find the mass of the two stars combined. So we're going to kind of have a modified version of our Kepler's third law. So when we did this with the solar system, we just had a cubed equals p squared. And that's because we were only worried about the mass of the sun, and the sun has one solar mass. So we were essentially just multiplying p by 1. Now we're looking at other stars, so we have, instead of multiplying by 1, we're going to be multiplying by the sum of the masses of the two stars. So this is our new way of writing Kepler's third law that relates the separation, the semi-major axis of the star's orbit, the period of the star's orbit, and then the masses of the two stars combined. And this is kind of the best way we have to measure the mass of a star, is by looking for binaries and then using this relationship between period and separation to find the sum of the masses. So what this might look like, if you can find two stars that are orbiting each other, when they block the light from each other, that'll tell us, that will change the light that we see. So we will, when we see both stars, when neither star is blocking the other, so when we get the total light of the two stars and we see a maximum brightness. When the fainter star moves in front of the brighter star, the faint star blocks the light from the brighter star reaching us, and we see a dip in the brightness of the binary system. So it gets fainter when the fainter star is in front. And then when the fainter star is behind the fainter star is behind the brighter star, there's another dip in the brightness. It's not as deep though, because we're blocking the light from the faint star, but we're still getting all of the light from the bright star. So we see another dip. And then again, as they continue to orbit around, we get an eclipse depending on which star is in front and which star is behind. So you can measure the period of a binary system, an eclipsing binary system, by looking at the amount of time between the primary eclipses. And that will be our period, because we know that will be the amount of time it took the smaller, dimmer star to go all the way around the bigger, brighter star. Measuring the semi-major axis can be a little bit more tricky, because you'll need to actually be able to see the two stars and like see their angular separation in the sky. And then if you know the distance to the two stars and you can measure the separation of the two stars, you can use a little bit of trig to find the actual separation of the two stars. So just really quickly draw this out as best I can. So if we know it's a really bad straight line, but if it was a straight line, if we know distance and we have our two stars orbiting each other, and we can measure the separation the angle of separation, we can use that to measure the actual separation, which is going to be 2 times the semi-major axis. And that's just because if I had drawn this line better, let's try that, we can see that this is going to be a nice right triangle with our tangent of this angle equal to the distance to the system, or the semi-major axis divided by the distance. So tangent of theta is going to be equal to opposite over adjacent, A over D. So we can use that angular separation that we can measure to find, if we know the distance, we can find so we can measure the angular separation, we can find the semi-major axis. And then we can plug both those things in to Kepler's law to find the sum of the masses. So, any questions about that? Go ahead and erase my drawing. Clear. We can also get some information about the radius of the stars in a binary system, because if we know how fast the smaller star is moving around, we can use the amount of time it takes for it to move across the larger star to figure out the radius of that star. So if we know velocity and we know time, then you can measure a distance traveled. So if we know how fast the little star is traveling, we can measure how long it takes to move across the entire size of the larger star, and that'll give us the radius of the larger star. We can also use how long it takes for the little star to move from not blocking the large star at all to totally blocking the large star, and that'll tell us information about the radius of the smaller star. So on this plot, the amount of time that we're in the primary eclipse when the smaller star is in front of the larger star will tell us about the radius of the large star. And the amount of time it takes for the small star to move in front of the large star, so the time it takes to go from total brightness to the lowest point in our light curve, will give us will tell us information about the radius of the small star. So this is one of the best ways to get the radii of stars when we can observe binary systems. And this is another thing, in the variable star lab, you look both at cepheid variables and at binary star systems. So you'll get to play around a little bit more. If you choose to do that lab, that will be a good way for you to see exactly how we can use binary star systems to measure masses and radii, and then actually get a little practice of that yourself. I think there's also a few homework problems that touch on this as well. So if you want to practice that, those would be good places to do that. And we are about 2 minutes till class is over, so I think this is where we're going to wrap up. If anyone has any questions as we go, either about this or anything else, feel free to ask them now. And if not, have a good weekend, and I will see you on Tuesday.
Thank you.
Thank you.
Thank you.